Hello, my name is Eridan Domoratskiy, and I'm going to present here my work with Dmitri Kosarev and Dmitri Boulytchev about empirical study of rational tree unification implemented in miniKanren'. Motivation. Our motivation is simple. We just want to use miniKanren' to infer recursive types. And we have globally two options. One of these is just re-implement unification in terms of miniKanren', and the second one is to extend miniKanren' interpreter. Previously, we already have presented a way to to extend miniKanren' using some non-relational way, using hooking and occurs check. It looks like that. So if we have a favor of unification due to recursion, we allow user to provide an alternative answer, and it works, but poorly. So now we want to try to implement complete unification for rational trees. And the second small motivation step is because some relations may become slower because of occurs check. Okay, what about history? And we have occurs check, and some provoke interpreters have no. We know that this isn't sound, and because of this, when Kosarev presented his rational tree model that is just Herban tree model, but with low to recursion in trees. Okay, what is rational tree? Rational tree is just like infinite Herban tree, but where we have only a finite number of subterms, subtrees. Okay. How we do unification? We have studied already existing unification algorithm and reformulated it in some more convenient terms. First of all, instead of substitution, we need to introduce equation systems because we need to allow recursion that isn't possible in substitutions. Nextly, we need to define some intermediate terms. First of all, we introduce head trees. That is just a functional symbol applied to variables. Equation is some construction like several variables equates to one of them and possibly to a head tree that is right-hand side. Equation system is just a finite set of equations with disjunctive left-hand sides, and additionally we need to use state to introduce fresh variables. Okay, we need to define some basic operations. First of them is union. Union is a function that unions two equations in the given system and return a pair of right-hand sides. Equations are identified by one of variables, and if there isn't such an equation, we need to assume that there is a trivial one. Okay, let's consider an example. If we need to union variables x and y in empty system, we just get a system with one equation with unified unioned variables on the left-hand side. Similarly, if we have already some equations, some different equations for x and y, we just here we union x with z. We just add z to left-hand side of existing equation of x. And finally, if we have, if we need to union equations that both have associated right-hand side head 3, like here we have f of y and g of z. We union them and preserve. Oh, I'm sorry. Preserve one of right-hand sides, but return both right-hand sides as a result of union. And now we can start defining our unification algorithm. Is the first two rules acts for two variables, and in the first case, if we have union to variables and it doesn't return right-hand side, it means that union was already does all work of unification. And if it returned right-hand sides, pair of right-hand sides, we need to just unify them. So the main point here is that we firstly union variables, and nextly we unificate them right-hand sides, unlike conventional unification algorithm. Okay, I think yeah. Next, we need to define more basic operations. Find operation just returns right-hand side of an equation. So if we have one system of equations, we may we may get first equation by variables x and y, and second equation by z, and something else non-existing equation will return for us trivial one. Okay, and bind is just a function that allows us to replace right-hand side of equation. Okay. Okay. Next, two rules of unification is what we need to do when we faced with one variable and one non-variable tree. Firstly, we need to find the right-hand side by variable x, and if there is right-hand side already, we need to just unify it with the given second tree, and if there isn't one, we need to bind the given variable with the given tree. And there are caveat, so we need to split the given tree on intermediate equations because we may get a non-head tree, but we need to place in the equation system only head trees. Rules for them for this looks like that. So we just when we have already right-hand side, always easy. But if we don't have, we need to introduce fresh variables, them bind, then unify these fresh variables with subterms, subtrees of the given tree. Okay, and finally, we need to swap arguments if it's x and t2. And finally, like in the conventional algorithm, we forbid different functional symbols, and for same, we just unify arguments. Okay, let's consider an example. If we have such a query, like on the screen, we will hang in a conventional algorithm. Why? After the first two conjuncts, we have a substitution like that. And when we try to evaluate the last conjunct, we will hang because of nature of system, or not nature of substitution. Firstly, we find x. Secondly, we unwrap f, find y, unwrap f, and loop. In our algorithm, we firstly consider first conjunct. It works like that. We need to add an equation for x firstly, but we have subtree here. And because of that, we need to introduce a fresh variable and unify it with this subtree. Nextly, we unify, and finally, we need to just union a fresh variable x2 with x, and we have a system like that. So we have splitted this complex tree on two equations. Similarly, we may solve a second conjunct, and finally, when we need to solve the last one, we firstly find x in system. Nextly, we unwrap f, and now we firstly union x1 with y. Now we just unwrap, union, unwrap, union, but we don't need to union something here because x1 was already union with y that was already unioned with y2. Okay, I think we may continue. And an important feature of rational trees is having finite representation. Finite representation is just a graph graph that consists of tree and possibly links to some trees, back references or cross references to compress representation. The number of nodes in the minimal representation always equals to the number of different subtrees. And every rational tree have infinite variety of finite representations, obviously. We use mu notation for finite representation of rational trees. To do this, we introduce a new syntactic form to allow back references in terms. For example, mu x f of x represents this tree, this minimal representation exactly. Just mu x. Oh no, I'm sorry. It isn't. I'm sorry. It's a different tree. Okay. Mu syntax isn't used inside of solver, but we need to use it to produce answers because it's only a way to represent rational trees as terms, as finite terms. Okay, for example, we may consider variety of representations for one rational tree, and we may see a problem here, but it doesn't. Oh, I'm sorry. Okay. Finally, how we get these terms? Given the system and the variable, we need to extract mu notation representation for x. Similarly to substitution application, we need to traverse system of equations, but we need to track encountered variables, and when we have encountered one variable twice on the path, we need to don't extract it twice, and then on second place we need to just return x or the variable, and on first occurrence we need to wrap it in a mu binder. For example, if we have such a system and want to get mu image for x, we will just unwrap firstly x, get f of x1, unwrap x1, get f of x2, and unwrap x2 to x, and we already seen it. Because of that, we just place here x and wrap the whole term in mu x. Finally, we have implemented this algorithm in miniKanren in several ways, and key point here that if we have algorithm that don't hang on recursive terms, we may consider a different unification when we works only with finite carbon trees, but don't do a cross check on every step, because we may work with not only finite terms. And we have considered some ways to implement it. Trivial one is just like a classical. Simple is we check variables right after the wall unification. The wall one unification conjunct was processed. Full is checking after the wall run. Multiplicative is similar to full, but additionally we do cross checks every m steps, where m is doubled after every cross check. And finally, square root is like multiplicative, but m not doublet, but is assigned to be a square root of size of equation system, and we don't check the all of variables, but only introduced from the last, no, not introduced, unified since the last cross check. And all of these ways shows demonstrated the worse performance than trivial. Finally, we have evaluated our unification algorithm using our type constraint solver, and for majority of tests, nothing changed. Here we may see these tests not changed because of logarithmic scale, but for slowest test, we have reduced time from 21 seconds to 8 seconds. Here we may see results in a short list. Thank you for. I am ready to answer your questions.
Thank you, Eridan. We have time for one small question.
Do these rational trees, do they have any correspondence to tree autonomy?
Could you repeat? I don't hear.
Do these trees have any correspondence to tree autonomy? Do these trees have any correspondence to tree autonomy?
This sounds like it might be a longer explanation.
I think it could. I think I don't. I cannot answer in time. I think it must be later. I'm sorry.
Any other questions? All right, let's thank Eridan for his talk.